Hello everyone. So in the last lecture we discussed or started discussing the determination of weight average polymer molar mass using static light scattering technique. So we will continue our discussion today and we will conclude it. So in today's lecture our discussion will be focused around first going through the light scattering behavior of dilute solution with containing large solute molecules. So that is where we left off in the previous lecture and we will start from there. Then we will focus on the effect of molar mass dispersity. So in the last lecture the expression that we had derived for solution of large solute molecules, that was for solute molecule which has a unique molar mass. Now we know that for polymer solutions the polymer chain lengths will usually be different and there will be a distribution of polymer molar mass. So the effect of this dispersity or distribution of molar mass or chain lengths, that how that is accounted for, that we will discuss. And after that we will talk about an elegant way to plot this light scattering data in a 2D plot, and through that how one can determine the weight average molar mass as well as some other properties of the polymer. So this plot is referred to as Zim plot, so we will discuss that in detail, and we will conclude by just talking about a few considerations regarding static light scattering measurement, and just briefly talk about some other alternative methods that are also available which are based on scattering, but this scattering is not of light but of other kinds of radiation or particles. So we talked about the fact that light scattering takes place when given sample or collection of molecules is exposed to incident radiation. And finally towards the end of the last lecture we talked about light scattering from solutions where the solute molecules have large dimensions. So when we say large, we mean that the solute molecules have dimensions which are of the order of 1/20th of the wavelength of the incident radiation in the solution phase. For the case where the solute molecules are large, the particle scattering factor was introduced, and this was introduced to account for the fact that for large solute molecules scattering, these molecules cannot be considered point scatterers anymore, and scattering can take place from different parts of the same molecule, and interference can take place between the scattered radiation from the different parts of the same molecule. So to account for such effects, this particle scattering factor p theta was introduced as the ratio of delta r theta by delta r at theta equal to 0. So here delta r theta is the excess Rayleigh ratio as measured at a scattering angle theta, and this denominator is the excess Rayleigh ratio measured at scattering angle theta equal to 0. Now this particle scattering factor p theta, we discussed that at very small scattering angles which corresponds to what is called the Guinier region. So in Guinier region the particle scattering factor p theta, the expression for p theta basically becomes independent of the shape of the molecule. In the Guinier region which corresponds to the condition that this q times Rg square to the power half is less than or equal to 1. So in this region the expression for p theta is independent of the shape of the molecule and is given by 1 minus q square Rg square by 3. So here we discussed that q is the what is called the scattering vector, and it is defined in this fashion. So it is 4 pi n naught sin theta by 2 by lambda, and as is obvious the units of the scattering vector is inverse of length. The Rg that we have, we discussed that the Rg is the radius of gyration of the molecule. A given polymer molecule can adopt different conformations at different points of time. So the angular brackets here represent averaging over the different conformations of our solute polymer molecules. In the Guinier region where this general expression for p theta is valid shape independent expression, we can also find out the expression for 1 over p theta. So we will see that this quantity 1 over p theta, or the reciprocal of p theta, appears in the scattering static light scattering equation. So, if p theta is given by this equation, one can approximately write 1 over p theta as this 1 plus q square rg square by 3, provided the assumption that this quantity is much less than 1 is valid. So, if this condition is valid, then this equation basically follows from the simple binomial expansion of 1 over 1 minus x. So, this also we discussed in the last lecture, and the light scattering equation for scattering from dilute solutions of large molecules is given by the expression here, where this 1 over p theta term is the extra term that appears in comparison to the expression that we had for small solute molecules. We can just substitute instead of 1 over p theta, we substitute this quantity here, and q is given by this expression. So, that substitution along with substitution of this in place of 1 over p theta, that gives us this term. So, the overall expression for static light scattering from dilute solution of large molecules is what is presented here. The expression that we have here, we see that the quantity m that appears here, that is the molar mass of the solute, and this equation that we have is still valid only when the solute has a unique molar mass. So, till now we have not introduced the fact that in case of polymer solutions, the polymer chains can have different lengths, and there can be distribution of chain lengths and molar mass, and hence there will be an effect of this distribution or dispersity on the static light scattering expression. Now, let us see that in the case of polymer solution where molar mass dispersity will almost always be there, how this expression changes, and we will see that the expression does not change as such in form, only change that takes place is that this m, the unique molar mass that we have in this case, gets replaced by the weighted average molar mass. So, in the next few slides we will see how that effect of molar mass dispersity can be accounted for. So, again we start with our equation for Kc over delta r theta, the basic equation for static light scattering, where because the scattering is from large solute molecules, we have this 1 over p theta term as well. Now, let us consider a simple case of infinite dilution. So, infinite dilution means that the solution that we are considering is not just dilute, but it is highly dilute, so that the concentration C tends to 0. Okay. So, the discussions that we have had till now correspond to dilute solutions, and now let us consider that in the limit of infinite dilution. Okay. So, in that limit, when C tends to 0, in this expression here, the second term onwards, all those terms will drop out because all those terms contain C, and as C tends to 0, those terms will become negligible, and we will be left with just these terms as C tends to 0. So, if we have just these terms, we can rearrange them and get an expression for delta r theta as k C times m times p theta. So, now this is again an expression that is valid for large solute in a solution, which is scattering an incident radiation, and which the solute has a unique molar mass. Now, let us see that if instead of the solute having a unique molar mass, if there is a molar mass distribution of the solute molecules, then how that can be accounted for. If we have in our solution polymer molecules of different lengths, and obviously if the chain lengths of the molecules are different, their molar masses will be different as well. So, if we have polymer molecules of different lengths and different molar masses, then for polymer molecules of a certain chain length or a certain molar mass, we can define the excess Rayleigh ratio specifically for each type of these polymer chains having different lengths. As we discussed, if there is a distribution of chain lengths or molar mass, then for each polymer chain length or for each collection of polymers molecules having a certain molar mass, a corresponding excess Rayleigh ratio delta r theta I can be defined. So, here I, the subscript I denotes particular collection of polymer molecules which have the same molar mass or same chain length, and we'll have different such collections. So some polymer molecules, let's say for example, might have chains containing 200 repeat units, whereas we can have some other polymer molecules present in the same sample having 250 repeat units or 225 repeat units. So this I corresponds to a collection of polymer molecules in the solution which have the same chain length and hence the same molar mass. So if we consider the definition of each of these terms in this expression here, so if we are talking about the contribution from polymer molecules of a certain molar mass, then correspondingly on the right hand side also we will consider the concentration of only those polymer molecules Ci whose molar mass is Mi, and for these polymer molecules with molar mass Mi, the corresponding particle scattering factor, let us say, is pi theta. So as we discussed, this delta r theta I in the expression is the excess Rayleigh ratio due to the Ni moles of polymer molecules of a certain molar mass Mi that are present in a volume V of our solution. So here small ni as per the notation that we have chosen, small n represents typically, small ni represents typically the number of moles of polymer molecules of a certain molar mass which is given by Mi. So similarly Ci is just the concentration of these particular polymer molecules having molar mass Mi. So it is important to note that in our polymer solution we will have polymer molecules of different chain lengths, and the Ci, let us say, corresponds to the concentration of a collection of polymer molecules out of the total solute molecules present, whose molar mass corresponds to Mi. Similarly this pi theta is a particle scattering factor for polymer molecules having this molar mass Mi only. Now let us see how this concentration Ci, whether we can write this in terms of some other quantities. Okay. Ci, the concentration that we have defined is in terms of mass per unit volume. So the mass of the polymer molecules having molar mass Mi divided by the volume of the solution. So that gives the concentration, and that's what we have written here, Ci equal to Mi by V. Now this total mass of this polymer molecules of a certain chain length and having molar mass Mi, that will be given by the number of moles of such chains or such molecules multiplied by the corresponding molar mass. So that is Ni times Mi. So this Ni times Mi will give the mass of this particular collection of polymer molecules, and hence Ci we can write as Ni Mi by V. And if we substitute this expression for Ci in the delta r theta I expression, then the expression for excess Rayleigh ratio for this polymers having molar mass Mi, that will be given by this relation here. Now we can see that we have two Mi terms present here, one here and one here. So we can combine them, and the expression for the excess Rayleigh ratio becomes K over V Ni Mi square pi theta. So here K, as we recall, is optical constant, V is the volume of the solution, Ni is the number of moles of polymer molecules having molar mass Mi, and pi theta is the particle scattering factor of polymer molecules having molar mass Mi. So now the delta r theta or the excess Rayleigh ratio for a particular scattering angle theta for the as contributed by the all the solute molecules together, that we can write as a summation of delta r theta i's. So where summation is over this subscript I, and this corresponds to summation over all the different chain lengths of all the different polymer molecules having different chain lengths that are present in our solution. Let us say we have a polymer solution which contains different lengths of chains. So we have chains having lengths of 200 repeat units. So let us say we will call them 200 mer. We have 225 mers also. So this we are just considering as an illustrative example. Let us say we have 250 mers. So these, let us say these three are the different chain lengths that are present in our polymer solution. In that case, if we have a polymer in the solution has these 3 different chain lengths present, then the I that we have will the summation will run over I from 1 to 3, where I equal to 1 will correspond to all the polymer chains having this 200 repeat units. I equal to 2 will correspond to all the polymer chains having 225 repeat units. So, delta R theta I will be the corresponding excess Rayleigh ratio as due to the polymer molecules with 200 repeat units, 225 repeat units and 250 repeat units respectively. So, to get the overall delta R theta for the entire collection of all the polymer molecules or different chain lengths present, we are just summing over the delta R theta i's, and that summation, if we just substitute this expression here for delta R theta I, then the summation will be over k by v ni mi square pi theta. Now, what we can do is just do some simple mathematical manipulations by multiplying and dividing the right hand side by certain quantities, and we will see that through that we will be able to extract some familiar terms from the expression that we have on the right hand side. So, of course, the k by v that we have here, this is a constant, does not depend on the index size. So, the optical constant or the solution volume does not depend on the particular polymer chain lengths that we are considering. So, that we can take outside the summation. And now let us see how we can multiply and divide by certain terms, so as to get some measurable and meaningful quantities from the expression on the right hand side. So, what we are doing here, if we just compare the expression for delta R theta from here and what we have written here, what we have done is multiplied and divided by this term sigma ni mi, and we have also multiplied and divided by this term sigma ni mi square here and here. Okay. So, if you just cancel these terms which have been both multiplied and divided, which have been used both in the numerator and denominator, then you will get back the original expression that we had. But we have, there is a reason behind writing in this form, and the reason is should be quite clear if you just take a look at this expression here, okay, and also the expression here. So, let us first consider this term. So, this sigma ni mi by v. So, if we consider the overall concentration of solute polymer solute molecules in our solution, and if we represent that by small c, then this overall solute concentration is what this term corresponds to, as is shown here. So, let us go through this step by step again. We are considering the overall solute concentration. So, that is the overall mass of the solute divided by the overall volume of the solution. So, total mass of the solute, let us say, is small m. So, this small m we can write as just sigma mi, where mi is again the mass of the polymer molecules having a particular chain length and a particular molar mass mi, capital Mi. So, if we sum over all such the mass of all such different types of polymer chains present or lengths of polymer chains present, then that will give us a total mass of the solute in our solution. And this sigma mi we can just write as sigma ni mi, capital Mi, where this mass, what we are saying is that mass is equal to the number of moles times the molar mass. So, we see that this term that we have here, there is nothing but the overall solute concentration. This second term, if we look at this term now, this from the definition of the weight average molar mass that we discussed in the very first lecture, introductory lecture. So, from that it should be evident that this expression here is just that of the weight average molar mass of our polymer sample. So, if we just recall the expression for weight average molar mass, that is sigma capital Ni Mi square by sigma capital Ni Mi, where capital Ni corresponds to the number of molecules, and equivalently we can write that as sigma small Ni Mi square by sigma small Ni Mi. This small ni corresponds to the number of moles. So, the term here we see it is the same as what we have here, that is a definition of the weight average molar mass. So, we see that by reformulating the expression for delta R in this way, we can actually obtain two measurable and familiar quantities in the expression. So, if we replace the first term here by concentration and the second term by the weight average molar mass, then the expression for delta R theta we can just write in this way. So, delta R theta becomes K times C times weight average molar mass times this bracketed quantity here. Next, let us see what this bracketed quantity is and how it can be related to again something some physical property of the polymer chains. Let us start again with the expression for delta R theta and let us focus on the bracketed term here. So, if we look at it closely, this is actually the bracketed term is a kind of an average of this quantity pi theta. Okay. So, this is an average of the of p theta actually over a sample that has molar mass dispersity and contains chains of different lengths. So, now this kind of average is referred to as the z average or the z average. This the z average is represented simply by an over bar over this p theta and a subscript z. So, when we say z average, actually this one can relate this z average to the z average molar mass that we have already defined in the previous lectures. So, we cannot actually calculate the molar mass, z average molar mass from this z average particle scattering factor, but we can draw an analogy between the way in which this z average p theta has been defined and the way in which z average molar mass had been defined in the first lecture. So, if you recall, the z average molar mass that we had defined as summation Ni Mi cube by summation Ni Mi square. So, if we compare this definition of the z average molar mass with this term here, so we see that there is a lot of similarity in that the denominator is the same, and the numerator here we can consider this numerator in this term to be Ni Mi square times Mi, and here we have Ni Mi square times pi theta. So, this is the z average molar mass or the z average of the molar mass of the polymer sample, whereas this quantity here is the z average of the p theta of the entire polymer sample, which shows a molar mass dispersity. So, now this p theta, we already know that the p theta or the p theta can be written in terms of q as well as the radius of gyration. So, now this p theta bar z that we have, that we can replace in the expression here. Upon doing that, the compact form of our expression for delta R theta is simply k times c times mw bar times p theta bar z. So, let us now focus on this p theta bar z a bit more, and earlier we have discussed that in the Guinier region at low scattering angles, this p theta can be written as 1 minus q square r g square by 3. So, if p theta can be written like that, the corresponding pi theta for particle scattering factor of polymer molecules having molar mass Mi, that also can equivalently be written as 1 minus q square r g square I by 3. And this will of course again be valid only in the Guinier region when this product of q times r g square to the power half, that is less than 1, and in this particular case this r g will be the r g I. So, for if the polymers have different chain lengths, their corresponding radius of gyrations will also, or radii of gyration will also be different, and this RGI corresponds to the radius of gyration for polymers of a certain chain length, which will correspond to a molar mass Mi. So, if we now we have this expression p theta, if we go back to the expression for this z average p theta, write that down here, then if we substitute this 1 minus q square r g square I by 3 in place of pi theta here, then we will end up with this term here. So, it has a summation over Ni Mi square multiplied by 1 minus q square rg square I divided by 3, and this whole term is divided by summation ni mi square. So, now if we take this summation sign inside the brackets, then what we will get is the first term will just be, we have a 1 here, so that will just result in a summation ni mi square, and this second term here will get ni mi square multiplied by q square rgi square by 3, and the denominator will still have ni mi square. If we rewrite it, if we divide both the terms in the numerator by this denominator, then the first term just becomes 1 because we are dividing ni mi square by ni mi square. In the second term, this term that we have, if we notice this q square and 3, these are constants, and these can be taken outside the summation sign. So, that is what we have done in the next step, and we have taken this q square by 3 outside the summation sign, and the term that remains is this summation ni mi square rg square I divided by summation ni mi square. So, again if we go back to the general definition of a Z average, so Z average molar mass we saw was summation ni mi square multiplied by mi divided by summation ni mi square. So, similarly we see here that this term actually corresponds to the Z average of the radius of gyration, okay, because we are in the numerator multiplying the radius of gyration of individual polymer molecules having a certain chain length by ni mi square, and dividing the whole, taking the summation and dividing the whole by just summation of ni mi square. So, this corresponds to the Z average of Rg, and that Z average of Rg will represent as Rg square over bar with a subscript Z. So, this represents the radius of gyration of our polymer sample, the Z average of the radius of gyration of our polymer sample. So, we have this expression for the Z average p theta in our case, and next let us see the case where we take the reciprocal of this Z average p theta. So, if we take the inverse of the Z average of p theta, then we can write this 1 minus q square rg square over bar Z by 3 as 1 plus q square by 3 times the Z average mean square radius of gyration. So, again this will be valid only in the case when this quantity is much less than 1, so that the binomial expansion can be truncated only after 2 terms. Once we have this expression, we know that the q, the scattering vector we have already discussed, is defined like this. So, once that is substituted here in this equation, then the 1 over p theta bar z, this term becomes equal to this 1 plus 16 pi square and naught square sin square theta by 2 by 3 lambda square, this whole thing multiplied by mean square radius of gyration and the Z average of that. So, now that we have this expression for this Z average p theta or the reciprocal of that we can incorporate back in the expression for the static light scattering that we had developed earlier for large solute molecules, and doing that will lead us to the an expression which accounts for the molar mass dispersity in the static light scattering equation. So, if we do that, the light scattering or the static light scattering equation that we end up with is Kc over delta r theta is equal to the product of these two terms, where the first term is first term basically contains the weight average molar mass as well as the concentrations. This second term contains the Z average mean square radius of gyration. So, we see that when molar mass dispersity or molar mass distribution of polymers is considered, that there are two changes that take place in the equation for light scattering from large solute molecules. One is that the unique molar mass that we had earlier gets changed to this weight average molar mass, and the radius of gyration that we had earlier, that was also just a mean square radius of gyration, that gets changed to this Z average mean square radius of gyration. So, these are the two changes that result from the presence of a molar mass dispersity or a molar mass distribution of the solute molecules. So, now that we have this expression, let us see how we can use this expression, how the data can be plotted to obtain quantities such as this weight average molar mass as well as the Z average mean square radius of gyration. If we again consider the static light scattering equation that we have developed just now, then this equation basically relates this quantity Kc over delta r theta to concentration of the polymer solution as well as the scattering angle theta. Okay. So, normally one would think that if we try to plot this data, so if we let us say perform scattering measurements of scattered light intensities with and how that changes with theta as well as concentration of the polymer solution. So, if we try to plot that data, one would think that normally a 3D kind of plot will be required where the z axis will contain this quantity and one of the axis x or y will contain c, whereas the other will have variation of theta. Because the right hand this quantity here actually is a function of two variables, concentration as well as scattering angle. So, normally 3D kind of plot is something that will come to mind if we want to plot this kind of a scattering data. However, the Zim basically proposed a very elegant kind of approach where the static light scattering data can actually be plotted on a 2D plot, and from there from that plot upon appropriate extrapolations the different quantities such as MW bar or this Z average mean square radius gyration or even A2, these can be obtained. So, let us see how the data is actually plotted on a 2D plot in a special way, so that we can obtain all the relevant quantities from such a plot. So, what is done is this quantity Kc over r theta, that is something so that this delta r theta is something that will be that can be calculated by measuring the scattered light intensities. So, ultimately in a light scattering experiment the scattered light intensities are measured and they are converted to delta r theta, and from there this quantity Kc over delta r theta can be obtained for scattering at different angles theta and also for scattering from polymer solutions having different concentrations. So, to construct this Zim plot, what is done is this Kc over delta r theta is plotted against a composite quantity sin square theta by 2 plus k prime c. So, we see that this composite quantity actually contains both theta as well as concentration c, and this k prime that we have here, this k prime is just an arbitrary constant, it does not have a physical significance as such, but this arbitrary constant should be chosen such that when the plot is actually constructed, then the data points are sufficiently well separated. So, the only requirement when choosing a value of k prime is that the data points on a Zim plot should be well separated. So, typically as a rule of thumb, if we are considering concentration in gram per centimeter cube, then k prime should be 100. Okay. So, k prime value will depend on the unit of concentration that we are using. So, if we consider this unit gram per decimeter cube, 1 decimeter cube is actually nothing but 1 liter. So, this is equivalent to a gram per liter kind of unit. So, now if we again take a look at the equation at the top here, and if we consider a certain limit when the concentration as well as theta both tend to 0. So, in the limit when scattering angles are very small, close to 0, and concentration is very small, so we have an infinite dilution kind of a limit. So, when both these conditions are applied simultaneously, then what happens is this Kc over delta r theta under the limit of theta tending to 0 and c tending to 0 just becomes equal to the reciprocal of MW bar. So, that we can see just by substituting theta equal to 0 and c equal to 0 in this equation here. Basically what we will see is that from the Zim plot after appropriate extrapolations, two curves or lines will be obtained. which when extended all the way up to x equal to 0 or all the way up to the point where they intersect with the y axis. So, they intersect at the common point, and that common intercept basically gives this 1 over mw bar. So, and that point corresponds to the condition where theta and c both are 0. So, this weight average molar mass one can obtain in this fashion, and graphically how that is obtained, that we will discuss very soon. Now, mathematically again let us see how this how one can obtain this second virial coefficient. Now let us consider the case where this Kc over delta r theta, what it reduces to when under the condition theta equal to 0. Okay, so C can have any value right now, but if theta equal to 0, then the expression that we get is this. So now let us differentiate this expression with respect to this quantity k prime c. Okay. So when theta equal to 0, all the points that are being plotted will correspond to being plotted against k prime c only, because with theta equal to 0, the sin square theta by 2 term here will also be 0. So in any case, let us see how, if we differentiate this quantity with respect to k prime c, what happens. So that derivative d of kc over delta theta delta r theta at theta equal to 0 with respect to k prime c, if we perform that differentiation, then this k prime can be taken outside because it is a constant, and we end up with just this derivative. And since the equation for kc over delta r theta at theta equal to 0 is this can be differentiated with respect to c to obtain this quantity. Now we have this derivative. Now let us consider the case when concentration tends to 0. So what happens to the value of this derivative when concentration tends to 0? So in the limit when c tends to 0, the value of this derivative will actually become equal to just 2a2 by k prime, because as c tends to 0, all these higher order terms will tend to 0. So again, just rearranging the terms, we get an expression for a2, which is k prime by 2 multiplied by this derivative in the limit c tending to 0. So we will see that this derivative corresponds to a slope of a plot on slope of a curve on the Zim plot, and this slope will have to be taken in the limit as c tends to 0 to obtain a2. Next, let us just also discuss how this z average mean square radius of gyration is mathematically obtained, and then we will move on to how graphically we can obtain these quantities. So again, for Zim plot we do this kind of a plotting or construct the plot like this. Next, if we consider kc over delta r theta, but now if we consider the quantity or this term in the limit when c is equal to 0. So at c equal to 0, this kc over delta r theta simply becomes the product of these two terms. So when c equal to 0, all these terms become 0, so we just have 1 over mw bar here, and in the second term there is no c, so it will remain as it is. So we get a product on the right hand side like this. And now let us differentiate this. So at c equal to 0, if we consider this composite variable, it will only consist of the sin square theta by 2 term, because when c is equal to 0, for that particular condition this k prime c will be 0. So now let us try to differentiate this quantity with respect to sin square theta by 2 and see what we get. So upon differentiation, this 1 over mw bar of course is a constant with respect to theta, and most of the other quantities in this term are constant, only the sin square theta by 2 term is there, so that has to be differentiated. So upon differentiation we just end up with this expression, because all the other terms, these as this as well as the radius of gyration, these are independent of theta. The derivative that we have here, that is given by this expression here, and again just by rearranging the terms we can obtain an expression for this z average mean square radius of gyration, and just rearrangement gives us this equation. So we see that we have this term multiplying or the prefixing this derivative, and this MW bar we already know from the common intercept that we just discussed previously, and this derivative that we have, this will correspond to the slope of the curve or the slope of the curve obtained by joining all the points under the condition c equal to 0, and that slope in the limit when theta is small, that will give us this derivative. Now let us see how. So mathematically we have discussed what all the three quantities that we can obtain from static light scattering, how they can be expressed mathematically, and let us now see graphically if we actually do a plot or construct a Zim plot, then how one can from that plot obtain the different quantities. So if we look at a typical Zim plot, there the Kc over delta r theta is plotted against sin square theta by 2 plus k prime c, okay. And in this particular example, this Kc over delta r theta has units of mole per kg and concentration is in gram per decimeter cube. So for that k prime that we have used is 0.1, okay, so that we have obtained a good separation of all the data points. So we do not see the data points be overlapping or being very close to each other in this plot, because the value of k prime that we have used is good enough to generate a good separation of the data points. So we actually, for a typical Zim plot, we actually get kind of a grid of data points, and what we can do is basically identify all the data points that have been plotted at some constant concentration, and also the data points that have been plotted at constant scattering angle theta. So if we consider all the points connected by the red lines here, these points correspond to plots which have been drawn at a constant polymer solution concentration. So these 4 points have correspond to a polymer concentration of C1. So these points were obtained at different scattering angles, keeping the polymer solution constant concentration a constant at C1. Similarly, these points are obtained at different scattering angles, but keeping the concentration C2 of the solution, and so on for C3 and C4. Similarly, one can also identify the points which have been obtained at constant scattering angle theta. So if we consider these 4 points here, so these are all obtained for solutions of different concentrations, but all at the same scattering angle theta 1. Similarly, these 4 are obtained or drawn at the same scattering angle theta 2, but the polymer solution concentration is changing. So similarly for theta 3 and theta 4 as well. So we see we have a grid of points, and we have just joined the points which have been obtained at for the same concentration, as well as points which have been obtained for the same scattering angles. So next what we need to do is extrapolate these points to limits where theta becomes equal to 0, as well as to limit when C, the concentration, becomes equal to 0. So if we consider extrapolation of the points corresponding to constant concentration. So if we extrapolate these points for C1 all the way up to a point which corresponds to scattering angle theta equal to 0, and we do the same for C2, C3 and C4 as well. So these blue filled circles that we have obtained are extrapolations of points obtained at constant concentrations to a scattering angle of theta equal to 0. So these points basically these points correspond to scattering angle of theta equal to 0 degree, and similarly all the constant theta points, they can also be extrapolated to the limit when C tends to 0 or the concentration tends to 0. So before that this theta equal to 0, the extrapolated points that we have, they can be further extended and extrapolated all the way up to the point where they extend with the y axis. So let us say they intersect with the y axis. So let us say they intersect with the y axis here, and similarly if we extend all the points corresponding to constant theta to a concentration C equal to 0, then let us say for theta equal to theta 1, the extrapolation gives us this point. Similarly for theta 2, this point, theta 3 we have this point, and theta 4 we have this point. So, these are all points at scattering angles theta 1, theta 2, theta 3, theta 4, but these have been extrapolated to polymer concentrations of C equal to 0. So, these correspond to C equal to 0, and again we can connect these points which have been obtained at C equal to 0 and extrapolate them all the way up to where they intersect with the y axis. So, if we do that, we see that the point at which the C equal to 0 line upon extrapolation intersects with the y axis is the same as the point at which the theta equal to 0 line upon extrapolation intersects with the y axis. So, this common point of intersection that corresponds to the condition of C equal to 0 and theta equal to 0, and we already saw that that condition basically corresponds to a value of 1 over m w bar for this quantity k c over delta r theta. So, this intercept that we have here, or the common intercept for C equal to 0 and theta equal to 0 extrapolated curves, that common intercept just gives us the reciprocal of the weight average molar mass. So, that is how we obtain the weight average molar mass graphically. Similarly, if we talk about A2, so A2 we saw was k prime by 2 multiplied by this derivative, and this derivative is nothing but the slope of this theta equal to 0 curve in the limit C tending to 0. So, the slope of this curve at small concentration values, that is what this derivative is, and so the slope of the curve here, that will allow us to calculate A2. Similarly, what we see is that the slope of this curve, so slope of the red curve which corresponds to C equal to 0 condition, that corresponds to this derivative here, and in the limit when theta tends to 0. So, that slope can be obtained from as a slope of this red curve here at small theta values, and that slope can be multiplied by this quantity here to obtain the z average mean square radius of gyration. So, we see that by constructing a 2D Zim plot in a clever way, one can actually obtain 3 different quantities corresponding to the polymer solution, which are highly useful. So, we have obtained the weight average molar mass, and that is the one which we were discussing so far. So, how to obtain the weight average molar mass, but in addition to that, the second virial coefficient as well as a z average radius of gyration can be obtained. So, apart from the molar mass, average molar mass, one can obtain a measure of the average size of the polymer molecules as well, which is quantified through the radius of gyration. Before finishing up, let us just discuss some points related to the measurements using static light scattering, and just quickly also we will also mention a couple of other techniques which can be used for determination of molar mass as well as radius of gyration. So, when we talk about static light scattering, to have a high sensitivity, one should have the intensity of incident light to be quite high. So, the incident radiation that falls on the sample should have a high intensity, and for that and it should have a fixed wavelength. So, a regular white light actually contains a range of wavelengths present. So, typically for static light scattering experiments, the light source that is used are monochromatic laser beam. So, this laser radiation, which is highly monochromatic and has a pretty much a fixed wavelength and has high intensity, that is used as the incident radiation for static light scattering measurements, and that allows a high sensitivity of the equipment. Apart from that, we see that this refractive index increment d and dc, that also plays a part. So, one would like to have this d and dc as high as possible. So, typically for conducting static light scattering measurements, the solvent chosen should be such that the polymer and the solvent basically have a high refractive index increment, so that again the measurements are the sensitivity of the measurement is high. Apart from that, of course, the sample has to be dust free, because if dust is present, then dust particles themselves will also contribute to light scattering, and that will of course lead to erroneous measurements of molar mass. So, the sample has to be entirely dust free, and typically the range of molar masses that one can obtain or the range of weight average molar masses that one can obtain from static light scattering measurements is quite wide, and it ranges from around 20,000 to over 5 million grams per mole. So, here the lower limit is basically because of the sensitivity of the equipment. So, if the molar mass of the polymer is too small, then the corresponding scattered light intensity produced might not be enough to be accurately detected, and also the molar mass increment D and DC, that also might not be sufficient for very accurate measurements if the polymer molar mass is smaller than, let us say, 20,000. And the upper limit 5 into 10 to the 6 that we have here, that upper limit is because of the fact that if the polymer molecules become too large, so let us say if the polymer molecules become comparable to, let us say, half the wavelength of the radiation in the solution or larger than that, then a large amount of destructive interference of the scattered light takes place, and there won't be it won't be possible to measure the or obtain the weight average molar mass. So, apart from static light scattering, there are actually some other techniques also that can be employed to determine not just MW bar, but also radius of gyration and other structural features of polymer samples at the nanoscopic level or nanometer level. So, a couple of important techniques with regards to that are small angle X-ray scattering and small angle neutron scattering. Theoretically speaking, the way we have approached the static light scattering, the theory that we have developed, similar theory can be used for small angle X-ray scattering and small angle neutron scattering measurements as well, but it is important to identify that the origin of the scattering, that is different in X-ray scattering and neutron scattering compared to light scattering. So, in light scattering we saw that the for a solution the scattering is because of the excess polarizability. In the case of X-ray scattering, the scattering is because of the difference in electron density, and in the case of neutron scattering, the scattering effect is because of difference in what is called the neutron scattering length density. So, although the origins of scattering are different, the theoretical treatment can be similar for small angle X-ray scattering and neutron scattering as we have done for light scattering. A couple of other things to mention about these techniques is that for small angle X-ray scattering, the X-ray used has a very small wavelength. So, in the light scattering, the wavelength is of the order of hundreds of nanometers, whereas in X-ray scattering the wavelength will typically be of the order of 0.1 nanometer or 1 angstrom. So, that basically restricts the use of this Guinier approximation that we have used. So, we have said that in the low scattering angle limit, or when Guinier approximation is valid, one can use an expression for p theta which is independent of shape of the molecule. So, in the case of X-ray scattering, because the wavelength is so small, the Guinier approximation is actually not valid if we are trying to explore or measure length scales which are above 5 nanometers. So, typical polymer molecules will have usually Rg larger than 5 nanometers. So, that is why X-ray scattering for such cases is not very useful. So, in that case one actually will have to know the shape of the molecule so as to get the actual p theta expression. In the case of neutron scattering, the wavelengths actually can be higher also. So, wavelength for X-ray scattering is around 1 angstrom. Neutron scattering, the wavelength can be from 1 angstrom all the way up to a couple of nanometers. So, for the neutrons having higher wavelengths, the length scale that can be explored in the Guinier region is actually of the order of around 20 nanometers. So, this length scale is actually good enough for measurement of small polymer molecules. Or small angle neutron scattering or SANS actually can be used for measurement of small polymer molecules having relatively low molar masses and sizes of the order of around 20 nanometers. One good thing about SANS is, or also about small angle X-ray scattering, is that these neutron radiation as well as X-ray radiation, these are these can penetrate up to great depths even in solid samples. So, that is why these techniques can be used for measurement of solid polymer samples as well. So, light scattering, as we all know, can only be used for measurement of transparent polymer solutions, whereas these SANS and SAXes can be used for measurement of solid polymer samples as well. So, that is an added advantage, and SANS in particular is a very versatile technique, and it is widely used for different kinds of measurements. So, with that we will conclude our discussion of measurement of weight average molar mass, where we discussed we focused primarily on static light scattering. In the next lecture we will discuss frictional properties of polymer solutions. So, there we will talk about the viscosity of polymers, dilute polymer solutions, and we will introduce the concept of hydrodynamic volume and what is called intrinsic viscosity, and we will see that the intrinsic viscosity actually can be related to the molar mass of the polymer, and the type of average molar mass that's related to the intrinsic viscosity is the viscosity average molar mass. So, we will also explore viscosity average molar mass and how that can be measured by intrinsic viscosity measurements. And finally, as a conclusion to that lecture, we will also talk about a technique which can be used not to obtain certain average molar masses, but to get the entire molar mass distribution of our polymer sample. So, such techniques are useful because full molar mass distribution is always more useful than simple numbers containing average quantities. And once we have the full molar mass distribution, all the averages that we have, whether it is Mn bar or Mw bar or Mz bar or Mv bar, all of them can be calculated directly from the entire molar mass distribution. So, we will also talk about how to measure the molar mass distribution of polymer samples, and with that we will conclude our discussion of molar mass measurement of polymers.